Sorry? Can you hear me?
Nice. Yeah, that's so cool. Okay. So, today we have an amazing and special, I know everyone's special, but this one's specific. We have a joint talk. We're going to do some fighting. Quote unquote. But I'm so happy to introduce James Kurlander and Pedro Bernardinelli.
You got it right.
So first up, James is a third-year PhD student at UW, working on beer frequency for the alert production scheme. Woo! Observatory to identify known asteroids and discover new ones. And in his free time, he likes to bowl and reasonably long board game events. Pedro is a bookstore built also at UW and completed his PhD from the University of Pennsylvania. And he's led numerous searches for distant objects in our solar system. He's also a heavy metal fan and doesn't know how many coffee makers he has in his house. Maybe around one. Okay, without further ado, I'll let them get to it.
Gonna start. Hello, everyone. As Sam introduced, I'm Jake. This is Pedro, and we are two members of the University of Washington Solar System Science team. We're going to be talking today about hidden planets in our solar system. I say hidden and not hypothetical because I believe in Planet 9, but we also have a Planet 9 detractor here, so there'll be some discussion, some debate, and we'll try to figure out whether or not there are further planets in our solar system beyond the ones that have already been discovered. So first, to prepare us, let's talk about the discovery of the known planets. There are 8 planets in our solar system, and we'll talk about Pluto a bit later. But the first 6, all the way out to Saturn, the planets are visible with the naked eye. And so since antiquity, since prehistoric times, folks who have looked up at the night sky have been able to see, identify, and recognize these planets, name them, tell stories about them, and everything else. But there's an additional 2 planets in our solar system that we know about. Uranus, which is discovered in 1781 by a British man, William Herschel, who, having a lot of money and free time, decided to spend his days as an amateur astronomer sanding down mirrors and building a telescope in his backyard. After repeated observation of the night sky, he noticed a dot moving on night after night after night, and wrote to the Royal Astronomical Society. Quickly, the planet was officially discovered, observed by others, and he was appointed Royal Court Astronomer by King George. Now, the planet hadn't been named yet, and so, having just gotten a cushy new job and a fancy new telescope and all sorts of things, William Herschel decided to try to name it George's Planet, after his new favorite person in the world. But the French, not loving King George, were not incredibly excited about that. And so there was a fight. And so after years and years, it was decided that the planet would be named after a Greek god, Uranus, like the rest of the planets. Now, Neptune was discovered about 70 years later, but its discovery was only made possible by the knowledge of Uranus and Newton's models and equations that described the motions of planetary objects. So instead of being discovered by pointing a telescope at the sky and finding a new thing that wasn't there before, Neptune was discovered by watching Uranus very closely. So by 1820, so 40 years after the discovery of Uranus, its orbit was really well constrained, and astronomers had published high-quality ephemerides, as we call them, or an almanac that tells you where to look for this planet every night very, very precisely. But throughout the 1820s and the 1830s, it was noticed that Uranus's orbit differed from the published expected positions by about 2 arcseconds per decade. So for those of you who aren't used to astronomer units, 1 degree is about the size of your thumb on the night sky if you hold it out at arm's length. An arc minute is a 60th of a degree, and an arc second is a 60th of an arc minute. So about 2 parts in 1,000 of a degree per decade. That's not a lot of motion. About 1,000. There we go. That's not a lot of motion, but the planet was observed for decades. This effect was found to be something real, something consistent, and something predictable. And so several astronomers, including Adams, a Brit, and Leverrier, a Frenchman, were put on the job of trying to figure out what was going wrong here. Some of the hypothesized reasons included maybe gravity is wrong, maybe Newton's equations don't describe the motion of everything in the sky. Other folks thought maybe the observations were wrong. Folks taking measurements through the telescopes back in the 1780s, they didn't know what they were doing. They were off by 2 arcseconds. We do everything right now. And the final hypothesized solution to the problem was that there was an additional mass in the outer solar system. And so everything in our solar system and everything in the universe tugs on everything else through the force of gravity. And the force that is exerted by every pair of objects on each other is proportional to the masses of those objects and the inverse square of the distance between those objects. And so if you have a set of objects and their positions, you can work out exactly what forces are applied to every object by every other object. And the motion of Uranus was consistent with one additional mass a little bit further out in the solar system. Adams and Leverrier both figured this out. So given the inner solar system is this tiny dot, Uranus's orbit here, 1830, 40, 50, 60, and the deviations of it from the expected positions. Leverrier hypothesized an additional mass right here. Adams hypothesized one here. And when Leverrier wrote to his friend in Berlin with a really great telescope, he, that very same night he got the letter, found Neptune right there. So Neptune's discovery was made as one person, a famous writer, described it with the stroke of Leverrier's pen. So this is not a discovery with observation, it's a discovery with theory.
And then, you discover a planet like this, you go ahead and you try to discover more. So something like 50 to 80 years later, once again, people were doing the same types of calculations because, that's like the first thing you learn in physics, how to do these things. And it turned out that, oh, hey, there's something else going on. There is another planet. So there was this guy, I completely forgot his name now, who proposed something like 10 different planets. And one of them, Planet X, because it was the 10th planet from his proposals, happened to be somewhat more correct than the others. And people decided to look for it. So if you go to Flagstaff in Arizona, there's this place called Willow Observatory. I'm wearing a t-shirt from there because I really like it. They have the Pluto Discovery Telescope. That's where Pluto was discovered. So the way that Pluto was discovered was same idea as Neptune. Some guy was looking for it, did some calculations, predicted an area in the sky, and etc. That guy was called Clyde Tombaugh. He had a high school degree. He didn't do undergrad or anything. He built a telescope basically from scratch with the infinite amount of money that Percival Lowell gave him. And eventually, he found this thing. He found Pluto moving. Those are the images there. It is very hard to spot, but there's an arrow there, right in the center. And he used this machine on the top that basically allowed him to blink images. He was looking at the images, this thing would blink them, and if something was moving, you could spot. And it took him months searching. He was almost giving up. But eventually, he found this thing, and hey, it was actually right at the position that was predicted by whoever predicted this, Pickering's thing, by Pickering. But it turns out that that was just dumb luck. Pluto is too small and not massive enough to cause anything in Uranus or Neptune's orbit. It was just by pure chance that Tombaugh discovered this thing, and this was in 1930, so 76 years later, Diego says, oh, hey, this thing is actually not a planet. Let's not talk about that. That's a very boring topic. Let's talk about real planets. And what Tombaugh didn't know is that he discovered this thing called the Kuiper Belt. And as always in astronomy, the name of the thing is not who discovered it, is not who first proposed it, it's someone else. Kuiper and others proposed that, oh, hey, these planets are forming, there is all this material, there must be more material because this is not an efficient process. When you're forming a planet, you basically need a lot of material, and lots of things don't actually become planets. So what people proposed in the 1950s or so is that there was this belt of material outside the orbit of Neptune, basically some leftover from planetary formation. We've discovered this thing in 1992. It's called a Kuiper Belt, or the Transneptunian region. And to answer one of the trivia questions, there are about 4,000 objects known in this region right now. So basically now, our current modern view of the solar system is that we have the 4 planets, the 4 inner planets going into Mars. We have the asteroid belt. Then we go and we have the giant planets from Jupiter to Neptune. Then we have the Kuiper Belt. But then, next slide. This is, let's see, early 2000s, 2010s, etc. We started discovering objects more and more distant in the solar system. It's kind of not a surprise. Every time there's a new toy, we discover more things. That's how astronomy works. If you look at the history of astronomy, since forever, that's how it works. And we started discovering things at the hundreds of AU. And cool. Hey, is this a new region of the solar system? What's going on there? And it turns out that these things, they're basically right outside the Kuiper Belt. They have very distant orbits. And there is some weird pattern in the orbits of these guys. And Jake will talk about that. And then I'll tell him why he's wrong.
So just before we get into the exciting, strange data, just a bit of theory background about why we care about things like the Kuiper Belt, the asteroid belt, and all of these little subplanetary objects, the asteroids and the comets that are swinging around our solar system in these big circular belts. So, as Pedro said, the process of planetary formation is inefficient. Not every object that starts out as a planetesimal or a little piece of the protoplanetary disk that accretes from dust into pebbles, pebbles into boulders, boulders into asteroid-sized things. A whole bunch of those things don't end up inside of the major planets. And the regions in which we find them today are not all of the regions in which they used to be. So the gravitational tugs of the giant planets make it such that if you're on an orbit really close to them or in certain configurations around them, that you're going to get tugged out of that orbit over, sometimes it's very quick, sometimes it can take millions of years, sometimes it can take billions of years. But since our solar system's been around for 4.5 billion years, things that are very slow end up happening. And so the processes that take unstable orbits, orbits that can't last forever with the giant planets orbiting as they are, end up cleared out. Now, we see certain structures in the solar system today, the Kuiper Belt, the asteroid belt, and these each have unique shapes and unique subcomponents to them. The Kuiper Belt in particular is made out of 4 or 5 different dynamical groups. We see a very tight belt, it's called the classical Kuiper Belt, as well as what we call the scattered disk, a large diffuse cloud of objects orbiting that tend to swing much closer in and go much further out outside of the sun. Now, we can learn about the processes that have acted on these planets over the last 4.5 billion years from studying the distributions and the shapes of these populations today. And as folks have done that over the last 20, 30 years, they found that the giant planets must have migrated in the distant past of our solar system. And so the places where the giant planets are today, Jupiter at 5 astronomical units, 5 times the distance of the Earth to the Sun, Saturn at 10, Uranus at 20, and Neptune at 30, this is not where these planets originally formed. And we can tell this because of, the colors aren't showing up great here, but there is a mixture of the types of asteroids sitting out in the Kuiper Belt today. And the only way that the simulation folks can end up with 2 separate populations mixing together is to start with 2 populations that form separately out in the outer solar system and have the planets migrate inwards. Migrate inwards over the course of the first 50 million years or so of the solar system, scattering, sending those planetesimals outwards and mixing them together.
And one extra detail here is that there are many ways that you can do this. One way you can do this is you have 4 planets form, these planets migrate, they go into where they are today, and there you have the Kuiper Belt. But also, if you put 5 planets, you can also reproduce the current known solar system. You only need to basically make sure that one of the planets gets kicked out eventually. So it is possible that our solar system had 5 giant planets initially. It's also possible that our solar system had 6 giant planets initially, and 2 of them were kicked out. Of course, getting 1 planet kicked out is already hard. Getting 2 kicked out, it's basically winning the lottery. So, but hey, if it reproduces the data, it reproduces the data, right?
So in 2004, the first of the truly distant objects in our solar system, Sedna, was discovered by Mike Brown and Scott Shepard. It's an incredibly distant object compared to the others in our solar system. It's out here at an average of about 540 times the distance to the sun as the Earth. The special thing about Sedna, now there have been other objects we've found that go out that far. The special thing about Sedna is that it doesn't come close to the inner solar system at all. Its perihelion, or its closest approach to our sun, is at about 76 AU. That's over twice as far from the sun as Neptune, about 2.5 times as far. So Neptune, as we've said, is probably what scattered the Kuiper Belt objects out to where they are. It's what shaped these orbits, but it can only do that through gravity. And gravity is only strong for objects that are pretty close together. So the previous picture of how the solar system formed, with the giant planets that we know of, scattering all these objects out to their current positions today, no longer holds up when we have a single object that could not have gotten to where it is without the giant, or with only the giant planets. Sedna on its own was a mystery, but the second discovery, 2012 VP113, wonderfully named, a second sednoid, as we call them now, an object that just doesn't come anywhere close to the sun, made this a really strong point. We need an explanation of how these objects got to where they are. The special thing about 2012 VP113, and the thing it set off in the literature, is that its orbit is very similar to Sedna's. So on this y-axis, we've got the argument to perihelion. This is one of the orbital angles. It takes a few different angles to describe the orbit. We're not going to put up any orbital diagrams, I promise. They're awful. But the point is, Sedna in 2012, VP113, the only 2 sednoids known at the time, share very similar orbits. And this isn't something that we expect to happen by chance. We expect these angles to be uniformly distributed. So we see over on the left, there's objects at every angle, -180, +180, everywhere in between. And that's what we see in the asteroid belt. That's what we see in the Kuiper belt. And all of these large reservoirs of objects, we expect a uniform distribution of these angles. But for the very, very distant objects, these 6 or 7, the angles are not uniformly distributed. Now, this is possible through, there weren't mechanisms at the time that were described that made this possible, but Trujillo and Shepard in their 2014 paper posited that a massive outer solar system perturber may exist. There might be some mass out there that's causing this. There are configurations of a giant object on an orbit that would allow this to be stable. And if you also have a single strong event that upsets the solar system, that moves some things out there, maybe a star comes really close to the sun and pulls a whole bunch of objects out of their normal orbits, maybe one planet is ejected from our solar system, that could create the configuration that we see today. Now, in 2016, somewhat more famously, Mike Brown and Konstantin Batygin noticed a second alignment in the orbits of these really distant objects. So this is a second angular parameter. That's the longitude of the ascending node. Again, not going to talk about what it is, but the 6 dynamically stable objects known in 2016 all share a very tight range of longitude of the ascending node. They're all angularly aligned. And unlike the previous parameter, this alignment means that they are also aligned in physical space. So the 6 objects known are these 6. 1, 2, 3, 4, 5, 6. Their orbits all point in the same direction into, space way out past our sun. This is not expected, and it's a pretty incredible coincidence that all 6 of these objects point in the same direction.
So basically, I was trying to remember what we were thinking of saying in this. So basically, if your objects are pointing somewhere and they're being kept somewhere, because we expect that over the 4 billion years of the solar system, even if these things form like this, they would eventually be anywhere. Because they are confined today, we need something that is acting on these objects today. So all of these crazy explanations that we talked about briefly here, something on the lines of, oh, hey, you had a cold stellar passage early on, or a rogue planet, and we'll come back to these ideas later. They don't work. The only thing that works is if you have a new planet on the solar system. And, well, people have been doing searches for things on the sky for a while now, for maybe like 300 years. And the reason, basically the only way of hiding a planet like this is if it's very distant, but also it has to be very big. If you had something closer, people would have detected it like 20 years ago, 30 years ago, or something like that. If you have something impossibly far, it will not do what we're seeing in these objects. So basically, what we need is something at the right direction and with the right size, and that would cause this. And back then, the idea was that this planet would be at around 500 AU away from the sun, so 500 times as far as Earth, with a mass of like 5 to 10 times Earth's mass. These numbers have changed, but this is the right ballpark. So basically, we're talking about something a little bit smaller than Neptune, a little bit bigger than the Earth, but 500 times further.
And the colors aren't coming through quite right here, but in this diagram, the hypothesized Planet 9 orbit is this one, heading the other direction out of the solar system. Planet 9 destabilizes the orbits near it, and so it sweeps out the solar system close to it, leaving only the objects distant from it. So we're expecting this sort of opposite side effect. Now, not everyone agrees with this interpretation of the results. We've got two surveys here, the Outer Solar System Origin Survey on the left and the Dark Energy Survey on the right. Pedro is the lead of the Dark Energy Survey, so let him describe this.
Yeah, so let me put on my nerd hat and talk a little bit about what's going on here. Of course, when someone makes a claim like, oh wait, there's a new planet in the solar system, people go ahead and try to verify this claim. And the strongest prediction of the Planet 9 hypothesis is that these objects, they are clustered in whatever angles we talked about. They're clustered in physical space. And of course, that's something we can test. This has a very clear, testable idea. These things are clustered. So let's come up with the opposite explanation. These things are everywhere in the sky. And if these things are everywhere in the sky, does this reproduce the data? And it turns out that this does reproduce the data. So here, this is the Outer Solar System Origin Survey, also survey. These lines here are where they point to their telescope. The dots that I can barely see, so you can see, are where these objects were discovered. Those are the objects we discovered. And if you zoom in this gray region, that is where we point to our telescope. And you can see that every single dot in there, it doesn't matter what the dots mean. That's basically where they could be or where they are. They're all also inside this region of the sky. So basically what's going on here, and that's why I'm the buzzkill of this conversation, is this is indistinguishable from things being anywhere on the sky. And I think that's where we start arguing, right?
Could be, yeah. So both the Dark Energy Survey and the Outer Solar System Origin Survey, both of them found results indistinguishable from a uniform distribution of these objects on the sky. But the original set of highly clustered objects were not taken from a single survey. That was the set of all known objects total. Now, ASOS and DES, they both had very small footprints. They both looked in, one in 5,000 degrees, one in about 100 degrees, so 1/8 of the night sky or 1/100th of the night sky. It's much, much harder to identify a bias across the whole sky if you're only looking in a very small area of the sky. So the two surveys that found uniform distributions of objects over the sky, they really found uniform distributions of objects over their limited survey areas. So by comparison, the original set of objects, which was discovered from every survey, looking anywhere on the sky, is potentially a less biased set of observations.
The flip side to this is that most of the discoveries have been made using Hawaiian telescopes, and it is virtually impossible to use telescopes in Hawaii in January. So why am I talking about January? Well, January happens to be the region of the sky that is up happens to be the other side of this figure. So basically, you're not seeing objects in the other side because basically no one can use a freaking telescope when this side of the sky is up. Of course, you know, that's kind of like cheating, right? We're just saying, yeah, we can't really find this thing, so there's nothing there. But yeah.
So I guess we got a bit ahead of ourselves, but the hope.
Yeah, we already started this. We're so excited about this, and we've been doing this for years that we got ahead.
We are going to discuss 4 topics today. 4 topics that either provide evidence for Planet 9 or against Planet 9. I'll be the pro Planet 9 side. Pedro will be against Planet 9. We're going to talk about the clustering of these extreme TNOs. We're going to talk about the data from the Cassini probe, the Saturn orbiter, and in particular its distance from the Earth, and how Planet 9 can be potentially learned about from that. We're going to talk about the generation of ETNOs, some orbits that should not be stable if you don't have a Planet 9, and finally, previous searches for Planet 9. Why haven't we found it yet? We're each going to try to take about 3 minutes to speak on our side per topic. We'll take 1 minute to respond to each other afterward, and each topic, after one person has spoken and the other has rebutted, we'll take 1 audience question for that person on that topic. So you can all take part. Put on your fighting gloves, and yeah, let's do it. These are Harlow and Shapley, right? These are there's a different great debate in the 1920s about whether there were multiple galaxies, and one. Huh? Oh, yeah. Shouldn't reveal trivia answers before they're all revealed. Anyway, I'll be taking the first topic first. This is the ETNO cluster. So. Just in the back, can you all see the colors here? No, okay. These are all of the extreme trans-Neptunian objects known as of 2019. This is from the review paper on Planet 9, Batagan 2019. There are about 14 of these total, and they're divided up into 2 colors. The ones that are on clearly stable orbits, orbits that, as far as the known planets are concerned, should not have changed over the lifetime of our solar system. So you can take a dynamical integrator, you can take the known planets, their orbits, and say, what would happen to this object over these 4.5 billion years? And 6 of these objects don't move at all. These objects should have been here since the start of the solar system and their birth. Those are Sedna here, GB117, this one, there, and there. So all of them are pointed out in this direction. There are some objects which are on unstable orbits, orbits that change over the lifetime of the solar system, and orbits that sometimes change over just tens or hundreds of millions of years. And those are the rest of them. Those are clustered much less, if at all, in this space. And so the fact that the 6 objects, which are dynamically stable, are all pointed in the same direction, the objects which we expect to have not changed their orbits are all pointed in the same direction, and the objects which are dynamically unstable, which might have been moved around a bit, are spread out all over the solar system, indicates that this clustering is not only real, but also not the effect of observational bias. So there's no way of pointing your telescope such that you're biased only towards dynamically stable objects and only against dynamically unstable objects. If clustering is the result of observational bias, then it should exist not only in one population, but all across the board. We shouldn't see any orbits up that way. But the fact that all of the stable orbits are pointed down and the rest of the objects are spread out is proof, I would say, that there is no, clustering is not the result of observational bias alone. There's intrinsic clustering in the ETNO angles.
You need to change your slide. Because I'll use my figure to show this. So, all right, so let me talk about this before I go to my slide. All right, so sure, the unstable objects, they basically are the ones where we don't expect to see these effects. So why are they also clustered? They're clearly also clustered with exception of a couple of them. And the reason why we're seeing this is, once again, that's where we're pointing our telescopes. We're pointing our telescopes so that this is where we can see things on the sky. We don't care about whether they're stable, or I think they use the term metastable or unstable or whatever. That's where we can find things. And you can see that basically there's a lot more going on here than just this whatever cherry-picked objects.
Next slide. Actually, one audience question. Any pro? Yeah, right there.
To join this debate, because there's something you've swept under the table. You said, well, maybe there's something wrong with gravity.
Yeah.
Today, I just submitted to the Library of Congress for copyright a book called Unraveling Gravity. I studied gravity in depth, and I want to tell everybody about it. I can see a different solution here. The gravitational field could be asymmetric toward where you think planet 9 is, with no planet 9 whatsoever. Here's a way to think about it that might cause you a little bit of pause, right? So dark matter is spherically distributed in disk galaxies. Newton's law of gravity is written as an inverse square law because an inverse square law is modeled after spheres. But if you use an inverse square law to study a disk, it gives you the illusion of a spherical halo that isn't really there. So you look out for dark matter and it's not really there.
So the distribution of anything on a galactic scale is going to look uniform at a solar system scale. The extent to which
Planet 9 could still be there, but I'm also not wrong with the large scale.
Also, I just want to point out that Newton's laws do not assume spherical symmetry. You can do Newton's laws on rings. In fact, that's actually how we model the orbits of the planets. If you're modeling the orbits of the planets over the scale of, say, 1 billion years, you don't actually care about where they are. You just care about their sum defects over a ring. So you can actually do Newton's laws in whatever shape you want. In fact, there are other things that look like Newton's laws. For example, electromagnetism. We can do electromagnetism on wires, and the math is identical.
Okay, so next we've got anti.
All right, so this is my favorite figure. The figure on the left is 2016. We had 6 objects. The figure on the right is 2021. I made this figure when I was defending my PhD, and I've been too lazy to update it. I also think that no one else has discovered another ETNO since then, basically because I'm not doing my job well. And, well, you can see that the clustering is gone. Things are everywhere on the sky. And they are preferentially down, yes. Once again, all surveys were pointing basically to this region of the sky, so that's why they're there. You can see all sorts of objects they would call stable or not anywhere. So, in other words, the clustering is gone. We have enough objects, we can just say that it's dead. We don't care about this anymore. And then Jake's going to tell me why I'm wrong.
I'd fall back to the point that ASOS and DES are pointing surveys in particular parts of the sky. And so if you start with a fair distribution of objects that looks like this, and you add highly preferential objects the other way, you might be able to end up with this. But I think it's going to have to wait until a uniform all-sky survey like LSST, which we'll get to later, before this can be confidently addressed. And
Do I have
an
a
audience
rebuttal?
question.
Do I have a rebuttal?
That was
to
my
you?
rebuttal.
Okay.
To
All right. So we have an audience.
Audience question for Pedro. Ishan?
Scans for which are not observed. Will there also be periods of the year where LSST would be unable to observe its light? So that observation bias continue. The heads for that.
Yeah. So the question, I'll just repeat it, and then the question is, if Hawaii is has weather conditions such that it's very difficult to observe in certain seasons, won't future telescopes like LSST that I'm hoping are going to provide a more uniform coverage of the night sky, won't they also be highly biased based on the seasons toward one part of the sky and against the other?
Yeah, that's a great question, and actually we kind of have the answer already. Since 2016, basically people have been doing surveys using Chilean telescopes. That's also where LSST is. And Chile is not as bad as Hawaii during the winter, so you can actually find things during the winter. In fact, all of the ETNOs that I found were observed during the Chilean winter. So that's actually also why they're somewhat in the same region in the sky. So while there is going to be an effect, it's going to be much less pronounced than currently. The other thing is that most surveys that try to actually discover these objects, they tend to point, and this is getting a little bit technical, they tend to point in opposition, which is where these objects are brighter. LSST will point everywhere in the sky. So it also basically takes away another effect that will be completely creating a bias.
One more good thing about LSST is that it has science goals for cosmology, so the study of really large structures all over the universe that require it to take uniform depth images over the entire night sky when all the images are added together at the end to form a single super, super deep, really high resolution map of the night sky. And so the LSST scheduler is doing optimizations to try to make sure that there is uniform coverage over the sky in ways that previous telescopes like Pan-STARRS, which discovered a whole bunch of these objects, was not doing because its primary job was to discover as many objects as it could. So LSST is going to have some built-in uniformity that's better than any previous all-sky survey. Okay, that is...
I have like 5 slides on this at the end.
Ah, yeah.
Don't spoil it.
Okay, point number 2, Cassini ranging. So here we have an inverse color image of the Cassini probe around Saturn. As was mentioned earlier, the giant outer planets have a gravitational tug on each other. Gravity is acting always between every pair of objects, and we can discover new objects by noticing accelerations in known objects. Now, we can discover Neptune by looking at Uranus, because Neptune's really big, it's pretty close to Uranus, but the smaller an object gets, and the further away it gets, the smaller that effect is. Now, the perturbations that were used to discover Neptune, those were observations made from the ground with a telescope. Uranus moved so much that it's visible with a telescope, even in the 1800s, that it moved a whole lot. There was a very strong force acting on it, pulling it away from the orbit it would otherwise have had. Now, Saturn is pretty far from Planet 9, and Planet 9 is smaller than Neptune, so we shouldn't expect a gravitational perturbation that's visible to the naked eye, or even visible with a telescope from Earth. But we have sensors that are way better than the naked eye or a telescope from Earth that don't require Saturn to move a whole Saturn radius before we spot the difference. We have an orbiter called Cassini. When I say we, I mean NASA. And Cassini stayed in orbit around Saturn for about 10 years. And during that time, its position relative to Saturn's center of mass was tracked very, very precisely, because the folks at JPL had to keep it in orbit. And it was sending messages from its atomic clock back to Earth. And so the JPL folks, using the time it took for that message to travel at the speed of light from the probe around Saturn to Earth, could check their positions. Now, they could check it only in one direction. They could check that they got the distance from the Cassini probe to Earth right. And they measured how wrong they were. These are called the residuals. Here are the residuals on the distance between the Cassini probe and Earth as a function of time. I said it's in orbit. That was slight misspeak. It crashed into the planet in 2014 when they crashed in on purpose. But you can notice a structure to these residuals. There's a curve. There's something going on here that isn't just random noise. It's not just occasional errors or sensor issues. There's some overall structure over the whole 10 years of Cassini orbiting Saturn that needs to be explained. And if you redo the position of Saturn, instead of using ephemerides based on an 8-planet model, but you use them based on a 9-planet model with the hypothesized planet 9 mass planet on a planet 9 orbit, the residuals flatten out. Planet 9, on its current orbit, explains a good fraction of the residuals in the Cassini ranging data. It's a subtle effect. It's not, doesn't bring every point right to the center. There are other errors, but a whole bunch of the mystery of why Cassini orbited Saturn in the way it did is explained by a planet 9.
So, Jake's sweeping something under the rug here. By the way, I just want to point out that we're friends. We're just making fun of each other. Jake, this is like 2 meters, right?
This is in meters. So negative 400 at the bottom, 400 at the top.
Okay.
Root
I
mean
thought it was actually a
square.
2 meter effect. Okay, so
No.
then never mind. I'm saying something stupid. I was going to make a joke that I thought it was a 2 meter effect, and I can even measure the position of my cats to 2 meter precision, but never mind. This joke doesn't apply here. Okay, so you are telling me that the position of Cassini was wrong by like 200 meters. Have you measured the full mass distribution of Saturn to do this? What happens if Saturn actually is weird and it has some like overdensities in one region or another? Or Saturn has a shit ton of moons. I think the last I checked was like 80 or something. Are you measuring the position of these moons to the precision that basically 200 meter precision, right? Do you have everything as well known that you can actually say that the only explanation is planet 9?
Okay, and then we get one audience question on Cassini ranging. No, it's the Paris Observatory Planetary Ephemerides group. So it's not my. I
It's not Jake's. It's
should have put a attribution on this plot. This is Fienga et al. 2016. Sorry. Okay. Any audience questions about Cassini? Yes.
Were there any outliers that were notable, like points that shifted more in the wrong direction?
No. So the effects are all very small over short time scales and very large over large time scales. Just adding something very far, it's adding a small force that is applied consistently throughout the survey duration. So nothing extreme is going to change when you add a large planet far away. Yeah.
So Moon was playing the face, so would probably not have the same synchronicity, same cycle.
Yeah, the effect of a close encounter with the moon should be a sharp change somewhere. So I don't see a big discontinuity that would be explained there, but
I see a big discontinuity in 2012.
no, it would shift and then stay. That's a single message thing. Okay, and then the anti.
All right, so there are some things that are easier to explain with a meme. Okay, so when people did this analysis, they completely forgot that a thing called the Kuiper belt existed, which is kind of the first thing that people should think about because that's why we're talking about this new planet. And if you consider the mass of the Kuiper belt, it turns out that the Kuiper belt has the same effect as planet 9 in the Cassini data. So the Kuiper belt has like 2% of Earth's mass. Pretty much all of this mass is in Pluto, Eris, and whatever other TNOs were mentioned in the trivia. I don't know all of them off the top of my head. And because of that, if you account for the position of all of these objects, you actually can also fix the residuals magically. Turns out there is additional mass in the solar system that we know of. Also, people have tried to investigate whether this is actually a measurable effect. Let's account for everything as well as we can. So the position of every single thing we know of in the solar system. And it turns out that if we assume that we have basically 10 years of data for things that we're measuring on the sky, plus all the data from spacecraft, plus everything else, the effect of planet 9 is not measurable. It's small enough that basically, in the best case scenario, we can't measure this.
You're right that the Fienga result was retracted. Totally agree with that.
It was actually not retracted. People
Or-
wrote papers saying he was wrong, which
one?
is
Yeah,
even
yeah.
worse.
But the degeneracy between the position of the Kuiper Belt and the potential Planet 9 also isn't evidence against the existence of a Planet 9. And there are, fingers crossed, hopefully some upcoming outer solar system missions that could provide much higher resolution positional data and be sensitive to much smaller gravitational perturbations. So again, looking to upcoming surveys and hoping.
Yeah, let me just make a comment here. Yeah, this is a fair point. Just because we can't see this effect doesn't mean that it's not real. Also, I'm joking here, but they were not that dumb. They included Pluto. But there's another Pluto-sized object in the Kuiper Belt, so they only included basically half of the mass from the two biggest objects. Yeah.
Any questions for the anti-Cassini ranging side? Yeah.
The difference between Planet 9 and the Kuiper Belt. The Kuiper Belt is a ring. Planet 9 is a single object going around. Wouldn't it be major when you're trying to
Yeah, so wouldn't a ring and a point mass have different effects? Wouldn't you see a different shape in the perturbations of the Kuiper Belt on Cassini and the perturbations of Planet 9 on Cassini?
Yeah, that's a great question. And the answer here is that it's because the majority of the mass of the Kuiper Belt is in only a few objects. So they kind of behave the same way as Planet 9. So can you go back a slide? If there is a real effect, the reason why you're seeing a spike here and a spike there is basically because it's Saturn's orbit and Cassini going around the sun with Saturn. Because the big objects in the Kuiper Belt, they're basically anywhere on the sky, and some of them are more massive than the others, that's also when you would see these spikes. So the effect of the Kuiper Belt is very similar because, once again, it's all a bunch of big things and then a ring much less massive than the big ones. Yeah, that was a great question.
So with that, we've covered 2 of our 4 topics. We're going to take the intermission, and we'll be back after trivia answers and time for everyone to get drinks for the next 2 topics and conclusions. Thank you.
Era pra ser zoeira, tá sendo zoeira.
Before I release you to go get beer or bathroom or just stretching, we're gonna do trivia answers really quick. So we have 1 big winner and 4, 5, 8. So some people did really well today. All right, here we go. 1. Which of these planets was not named after the Consensus, the Roman Olympians? It's Saturn. You didn't know. 2. How many times astronomers proposed a new planet in the solar system, and how many times have they been right? 10 proposals and 2 are correct. C. The planet Uranus was first discovered through direct observations. You should know that now. Question 4. The planet Neptune was first discovered through what? Mathematical calculations. 5. How many trans-Neptunian objects have we discovered as of July 2024? Around 4,000. Question 6. Which trans-Neptunian object is named after the early Roman god of the underworld? Orcus. I can't see, I'm blind. Okay, 7. Which of the trans-Neptunian objects named after the giant who tried to overthrow Zeus? That's bold. Typhon. D. 8. Which trans-Neptunian object is named after the Greek goddess who incited the Trojan War? Eris. 9. Please know this. This is Jake and Pedro. They're the ones that are fighting today. And 10. What kind of combat war requires engaging in civil discussions? And some name calling, not name calling. Light trickery. Okay, anyway. We have 8 people. Yes, so drum roll for our 8, please. Alright. In no particular order, Skycar. Woo! Back. Alright, we also have, I love this, bedazzled calcium. Nice. Okay, 2, the non-UW physics. I might have slight eyes over here. You'll get your prize at the end. And homesick subterraneous? Homesick person? Are you okay? Do you need help? Okay. Okay, and for our large winner, big prize, even though you all get the same prizes, but bragging rights, drum roll. We have the very unique team name. Team name, all right, good job, guys. Okay, so we will be back get beer, stretch, get food, whatever you need, and we'll be back in like 5-10 minutes.
Test, 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 test. In the back, is this good? Okay. So we've covered the clustering in angular space of the extreme trans-Neptunian objects, the most distant things we've discovered in our solar system. We've discussed the ranging data from the Cassini probe, these really, really precise speed of light measurements between an atomic clock and a second atomic clock. Next, on to the third thing we'll be discussing, the generation of strange TNOs. So we have discovered 3 at this point, but more hopefully coming soon, objects in the distant solar system. Sedna, the 2012 object, and one more in the last 5 years, which each have perihelia, so their closest approach to the sun, very, very distant from Neptune. Sedna is at 76 astronomical units compared to Neptune's orbit 30. So this is 2.5 times farther from the sun at its very, very closest point than Neptune, the only large gravitational perturber in the outer solar system. And the question is, how do you get these? What story can we tell about how the solar system formed such that these objects end up where they are without an extra planet in the outer solar system? And there isn't a story without other objects, without something that we haven't seen that gets you these objects. So the only thing that moves objects in the solar system, outer solar system at least, is gravity. Gravity is a force, and forces change velocities. They don't change positions. So you might be able to, when objects' orbits change, they never change suddenly and completely. Some point on that orbit has to stay shared between an orbit before a perturbation and an orbit after a perturbation. So the story of how you get an Kuiper belt object out into a sedenoid orbit is that first, while it's orbiting here in the Kuiper belt, where objects actually tend to be, Neptune perturbs its orbit, and it ends up on an ellipse that goes much further out and includes one of those points. And then while it's out there, a second perturbation happens that opens up its orbit and sends it super distant into the much, much further outer solar system. You need a story like that to explain these objects, and the only way to do that is by applying a force to these objects while they're 70, 80 AU from the sun, really far from Neptune. There's a second sort of strange TNO that we shouldn't expect to exist without Planet 9, and these are Neptune crossing ones that have very, very high perihelia. So it's not that we don't expect these to ever exist, but Neptune on its own is very bad at taking TNOs in the Kuiper belt out at 40, 50 AU, and simultaneously bringing their perihelion, their closest approach, well inside of Neptune, while also sending the aphelia, the farthest point, really, really far out into the outer solar system. And this is because Neptune crossing TNOs are unstable. If you're crossing Neptune's orbit, pretty soon you get kicked out of your orbit and into a new one. So Brown and Batagan, the Planet 9 guys, ran 2 simulations of a whole bunch of trans-Neptunian objects being perturbed, being moved around by Neptune and the whole solar system, all 8 planets. And this is the distribution of objects by semi-major axis, so their average distance, and perihelion distance, so their closest approach. And you find that the Neptune crossers pretty much all end up with really high perihelia, really high closest approaches, very close to Neptune's orbit. But if you add a Planet 9 to that simulations, if you add one more planet out on the orbit that they hypothesized from the clustering of these TNOs, you end up with a bunch more objects at much lower perihelia and a much more spread out set of objects. Here is the data for our actual solar system. We've got 17, 18 points on this chart. And just by eye, which of these 2 charts does it look more like? Are we living in a Planet 9 free simulation-like solar system? Or are we living in a solar system that looks a whole lot like the Planet 9 simulation one? You can't get these low perihelia extreme TNOs without something else going on. And so there must be a Planet 9.
Come on, Jake. Tell us the truth. The only reason... The only reason why you actually have 2 slides for this set of explanations instead of 1 for all the other ones is that between the 2 of us, we've discovered half of the objects in this plot. That's true. Sorry, not half, a third, right? Anyway. Okay, so yeah, that's a beautiful story, right? I like this story of, oh, you have this planet and it's forming all these distant things, and it's also injecting all these things towards the inner solar system, and etc. However, there are other ways of forming distant things. You can have the super hyperhuman objects. You can have them form through a flyby with a star. So you can have our sun or solar system pass close to a star early on in its history or in the last 2 million years. It doesn't really matter that much. If you have something like that happen, you will produce objects with very high perihelion. You will do some weird things to the Oort cloud. That's where the comets come from. You will do weird things to the Kuiper belt. And we know these encounters have happened. We know from measurements of the positions of stars and etc. that these sorts of things, they happened really in the close past, in the last 20 million years or so. We also know that when the sun was formed, there were many of these things happening early on. For the objects here, well, they're in a chaotic zone of the solar system. So what happens here is, because you have all the 4 planets, the 4 giant planets, we don't care about the other 4, acting on the orbits of these objects, this is a very chaotic zone. So weird things happen, and weird things like high inclination objects will happen. So basically, are you telling me that you've simulated every single possible orbit, input orbit to these things to tell me that this never happens?
Okay, one audience question about the generation of extreme TNOs. Yes.
For the scientific community studying this, where are they on this debate? You have a
Yeah.
or does it lean one way or the other for the whole community studying our solar system?
Do you want me to take this one?
Yeah.
I would say that things are changing. When this hypothesis was initially made in 2016 or so, a lot of people were very excited. It basically brought new energy into the field. That's also when I started doing things in this field, so I have a somewhat biased view here. Now, things have calmed down a little bit. Basically because we've been trying to find this planet for almost 10 years now. No one has found it. That's actually the next point we're going to talk about. And so people are kind of bored. However, and that's our last few slides, if only there was a project coming that would discover this thing. But yeah, I would say that nowadays, most people are, they kind of just ignore it. It's something that we'll know eventually, but people are not putting their money on or their careers on. I have to say that I'm being dismissive here on purpose, but this thing got me really excited. This was the first time that I actually started thinking about, wait, is this actually a real thing or not? And Jake and I are actually working on that. We've talked to the people who did the simulations, etc. And because we've discovered half of these objects, we can actually do this.
Next, we're going to have the anti-generation of strange TNOs argument.
That's my argument. You're cherry picking. You have something like 4,000 objects. Of these 4,000, there are like 15 of them that you can't really form. That's telling me that probably you missed something in your models. That thing may be Planet 9. That thing may be something else that you don't know about. So I guess the argument here is, how can you prove me that this is the only alternative? That's how you do things in science. You basically only know if something is right if there is no other way this could be wrong. So yeah, you're cherry picking.
So if we go back to this set of objects, these are Neptune crossing. These come close to the largest mass in the outer solar system. As far as outer solar system objects go, these are the least stable, the most unstable objects that we have. So you can't stay on a Neptune crossing orbit too long. You mentioned earlier, other hypotheses. Maybe something happened in the very early solar system that made an asymmetry. Maybe you get these from a one-off event in our birth cluster, our stellar birth cluster. If there was an event a super long time ago, you'd expect Neptune to have cleared these objects out. These objects can't survive on these orbits particularly long. And so this must be a pretty recent thing. Now, maybe there was a stellar flyby recently. Maybe a star passed in the last 100 million years. The Gaia space probe is doing a real good job as the European Space Agency probe of finding the positions and velocities of all the nearby stars to us. And folks are doing work to try to find exactly which stars passed us at what times and how close. And there isn't any hypothetical passage, as far as I know, and they can do this out at least a few million years. There's no recent nearby stellar encounter that could do something like raise TNO at 50 AU up to 1,000 AU in semi-major axis.
Do I have a rebuttal?
One audience question. Yeah.
Eccentric or something, Neptune and Uranus swap orbits, one that's further out than the other.
No, this is Pluto and Neptune. So all of the planets' orbits are super, super circular. Let's get back to the plot with all of the planets' orbits. There we go. Every planetary orbit is really close to circular. They're not all exactly circular, but eccentricity is very, very close to zero. Pluto is an outlier among the planets, primarily because it's not a planet, but you can think of it the other way as it's not a planet because its orbit is so strange among planets. It's on an eccentric orbit, which carries it out as far as 40 AU and in as close as somewhere in the high 20s.
It's like 26 or so.
Yeah.
Don't remember.
It's inclined out of the plane 10 degrees. All the other planets are very coplanar, and it's much, much smaller than any of the others. So it's Pluto that swings in and out.
Let me add something else here. One other thing about Pluto's orbit that's actually fascinating is that Pluto is in what we call a mean motion distance. So this thing means that basically there is a ratio on the periods between Pluto and Neptune. So every 3 orbits of Neptune, Pluto completes 2 orbits exactly. So this was kind of the first thing that made people think that there was something else going on in the outer solar system, and maybe that Pluto had a different formation history. Because it's very hard to form this thing that are called disresonances. And I think people only realized this in the 60s, so like 30 years after Pluto was discovered, because that's basically when astronomers started having computers. As I said earlier, you have a new toy, you find new things.
Okay. Then we'll move on to the 4th topic, previous surveys. So as Pedro said, a whole bunch of folks have been looking for Planet 9 since at least 2016, when the Brown and Batagan paper predicted its location in the sky really took off and got everyone really excited. Now, no one's found it, and so it's going to be pretty tough for me to make an argument about why it exists based on previous surveys. But instead, I'm going to try to make an argument about why it's really plausible that even though folks looked for it, they didn't find it. So I'm going to be saying that Planet 9 is really hard to find. Every asteroid that's been discovered, every object in our solar system that's been discovered, has been discovered pretty close to the sun. There's a single object out at about 130 AU that was found in 2021, but beyond that, there's nothing. Now we're looking, when we look for Planet 9, for an object that might be at 500 AU. It might be at 700 or 1,000 AU from the sun, depending on which of the hypothesized orbits you believe. This is really, really different from anything we found before. And one really important observable about minor planets, or major planets, is how quickly they move. So if you look at Planet 9, if you can see it, if it's bright enough for you to see, you're not going to see it move over the course of a night. The traditional way of finding objects involves repeatedly imaging the same spot in the sky and looking for motion. And we have these amazing automated computer systems that do this. None of them would have found Planet 9. And in fact, almost no astronomical survey that's been conducted was designed to find the sorts of things, or to find things that move as slowly as Planet 9, because for the vast majority of the time that these surveys have been developed, we didn't expect there to be a Planet 9. Additionally, it could be really, really dim. So the sort of plausible range of brightnesses for a 5 Earth mass thing hanging out somewhere between 200 and 1,000 astronomical units, it's between 16th and 26th magnitude. Now, those numbers are probably meaningless, so I'll try to give some context. Pluto is around 15. So if this object is really shiny, really close, really big, it could be just a little bit dimmer than Pluto. Now, we've pretty much ruled that out. It's a possible orbit and a possible size from all the previous information, but folks have looked over the sky with telescopes that can see well past 16th magnitude over and over again, so many times, including folks looking for Planet 9, that's eliminated. The best modern surveys, so that could have discovered Planet 9, the Dark Energy Survey, ZTF, the Zwicky Transient Facility, that's run out of Caltech, I think, and Pan-STARRS. This is the incredible asteroid discovering telescope in Hawaii that has all these observational biases because of Hawaii's weather. They've surveyed the entire sky to about 21st magnitude, and parts of the sky as deep as 25th magnitude. Now, Planet 9 could be as dim as 25th or 26th magnitude. That's about 100 times dimmer than the brightness to which we've surveyed the sky, and a little bit dimmer than even DES goes, if you imagine that it's a very dim planet overall. So TNOs can be very bright. They can reflect almost all the light that they receive. They can be very dim. They can reflect almost none of the light. There's a huge variation. And if you imagine that it has low albedo, it could be a very, very dim object. So it's one that we haven't looked for with most of our surveys. It's too dim to see with most of the surveys that have been conducted so far. There's no... not having found it is no argument that it doesn't exist.
Not having found it is also not an argument that it does exist. But anyway, I think this is a very fair point. And I don't actually have a rebuttal here. I just have a comment. You can't find what you're not looking for. And Jake is correct, and there's nothing to say here. People are not looking for this thing, or they were not looking for this thing until 2016 or so. Since then, people have tried, but so far we have not been successful.
One question on, yeah.
What kind of experiments have been devised in the last 10 years to decide whether or not it exists? I'm sure someone has devised an experiment.
Yeah, so for an experiment, you need data, and we've got 2 sorts of data we can try to work out here. One is, well, I'll say 3 sorts of data. One is direct observation. You can point a telescope at it and see it, and if it's 25th, 26th magnitude, the way we get there is by building bigger and better telescopes the same way that everyone's always trying to build bigger and better telescopes. Sometime in the next couple decades, we'll have covered the whole sky to 26th magnitude, but the only experiment we can do there is the same experiment every astronomer has always been trying to do. We could put a probe really far out in the distant solar system and notice how it's tugged around by different, the different gravitational forces that act on it. Right now, Cassini is the most distant orbiter of any object, and you need to be orbiting something to get really good positions, or to have several craft. There's a Uranus orbiter and lander that's being planned by NASA that might get funding. That would be a 2040s mission. So, it's an experiment. It's not easy to get something orbiting a planet in the very distant solar system. And then the last idea is just to discover lots of these potentially biased, potentially not biased asteroid orbits. And that's the same sort of experiment we're always trying to do, just find more objects.
Let me just add something here. Jake, can you go back to the clustering plots, whichever one of them? This one works. A few experiments that came up, let's see, I think we started taking it in 2019 or so we're analyzing the data now, is to point exactly outwards the cluster. So there are a few surveys currently happening that are doing that. It is hard because that's where the weather is worse and etc., but it's something we can do. So there are 2 big surveys that are doing this. One's called Classy. It's being run by some folks right north the border of us in Vancouver and Victoria. Another one's called Deep. It's being run by me. and a few others here in UW. We don't have our results yet, which is frustrating, but we will soon. And one of the things we're trying to do is exactly see if by pointing outside the clustering, we also see these objects. Okay, so my point here is very simple. Jake was saying that only like a few projects could have discovered it, etc. But that's not really true. Since 2016, everyone who has access to a telescope or data, for example, myself, have tried to search for this thing. And we've tried to search for this in the optical. So this is where DS is looking for objects, and each dot here is one realization of 1 and 9 from the model. So that's like 12% of the dots have been ruled out by the survey. Combining with ZTF and PenStars, which were the two other projects Jake was talking about, now it's been like 80% of the parameter space that's been ruled out. But also there are other projects out there. We've been talking about how this is hypothesis by Mike Brown and Constantine Battighi, and they've been using a lot of telescope time to try to find this thing, basically because if they find it, they get a Nobel Prize. So, it's kind of like a high-risk, high-reward thing. But also, people have tried to search this in other types of data, for example, infrared data or cosmic microwave background data. Those are types of data that people don't look for objects like this because they're looking for different types of structure in the universe. But it turns out that some of them are actually very nice for finding something like Planet 9, and no one has found anything.
I'd say that the any searches that are unsuccessful and that don't announce their results can't be taken as a scientific result. If it's not a published, stated non-discovery, then that can't be included. Now there are published, stated non-discoveries. If you do an experiment and you find a negative result, you publish that result. So if there's a point there towards plausible other folks who've been doing things with telescopes but not published it, I don't think that's valid. But the 80% of possible orbits and locations, I think that was assuming an albedo of 0.3. I think with extreme albedos, like you can see in some of the distant TNOs, some of them are just very, very dim and beyond what could be discovered with modern telescopes. Okay, any questions for the anti? Yes.
That's a great question. So the question is, why are we not using orbiting telescopes to search for this? There are two parts to this answer. The first one is the current telescopes that are in orbit, they're kind of not made to find things like this. So the two that everyone thinks about are the Hubble Space Telescope and the James Webb Space Telescope. These are meant for basically when you know where the object is, you point that telescope at it. So if you were trying to search for something like Planet 9 with Hubble or James Webb, that would take forever, like 100 years of telescope time to basically cover the same area that we've covered in 5 with this prime. This is kind of like a design thing. It's one of the big reasons why we put telescopes in space is to get very detailed images and other sorts of information out of these things. So it's kind of not worth it to use something like Hubble or design something like Hubble to search for this thing. The second part is, are there any planned projects that could do something like this? And there are a few things that could help. The first one that comes to mind is the Roman Space Telescope. This will be launched in 2027, if I'm not mistaken. And it's basically Hubble on steroids. It has a very similar design to Hubble in some aspects. It has the same mirror size and etc. But it will cover a lot more area in the sky, and it will cover more area than James Webb. So that's a more optimal telescope for searching for something like this. The other option that I completely forgot about until 5 seconds ago is Gaia. We talked about Gaia for measuring position of stars and etc. And Planet 9 is unfortunately too dim for Gaia. So Gaia would not have found it.
Okay, those are the 4 topics. So, moving on from Planet 9 itself, we're now going to discuss some alternative hypotheses about what could be forming the things we see other stories we can tell about the solar system that could produce the evidence we've been talking about, and then we'll conclude with what could be done with future ground-based observatories. So the first alternative hypothesis is a close stellar encounter. This has been proposed by a whole lot of folks as a way of moving objects around in our solar system. But the Jilkova group in 2015 proposed a really unique solution to the generation of these extreme TNOs, the generation of things like Sedna that orbit too far outside of our too far from the sun to have been generated from inside our solar system. Maybe those objects are captured from a close encounter so close that trans-Neptunian objects, or distant solar system objects from the other star, ended up stuck in our system, and perhaps some objects from our system ended up stuck in theirs. This would produce angularly clustered objects that could not get to where they are with gravitational perturbations from our planet. It is a pretty extreme scenario. Stars don't tend to pass this close to each other, and so it would have to be somewhat recent and very close in a way that makes it a less plausible story. But if we could get sample returns from these extreme objects, we could potentially do some chemical analysis and look at isotope ratios and work out if these objects did originate from our sun, or if they look stunningly different at the chemical level to all the other trans-Neptunian objects.
And sorry, let me just add something here. And also, you were talking about recent encounters, but distant encounters could also produce things like this in some cases. Sorry, not distant, I mean distant in the past, not distant far from the sun. And we now know that it is very likely that our sun was formed in a cluster of stars. So basically, a bunch of stars formed with the sun. And this is one of the ways that we can explain some of the features we see in the Kuiper node today. So it's possible, it's not impossible.
Second alternative hypothesis is an ejected planet. So this one actually rejects all of the arguments I was making before. It says there's no clustering, it's all observational bias, but there is a different effect that generates very similar data. So if you imagine that there was a fifth planet in our solar system in its birth in the first 50 million years of our solar system, 4.5 billion ago, and through planetary migration, that object started very close to the sun, and then moved out and out and out and out and out, scattering off of further and further objects, it would have brought a whole bunch of those objects with it. And as that object's orbit became more eccentric and more pointed in one direction, it would have biased the angles of objects in our early solar system in the exact opposite way. So the same thing Planet 9 we think is doing now, this planet would have done in the very distant past. Now we have great dynamical integrators. We can say, what would an object on this orbit have done over the last 4.5 billion years? And if you take all of these test particles on the left, which were generated in Yukon Huang's simulation, 2024, real recent paper. If you take those, generated by an actual planetary escape in a simulated solar system, and you integrate their orbits for 4.5 billion years, the lifetime of the solar system, you end up with a slightly non-uniform distribution out here that does match pretty well what we see today. And in particular, the three objects in our solar system that are discovered that are in this sort of special class, very high Q, very high perihelion, those three objects, if we wind back the clock, we do reverse integration, we take their positions today, which are not very closely aligned, and we wind the clock back 1 billion, 2, 3, 4, 4.5 billion years, we find that they all line up. That's the same sort of argument that was made to justify the Planet 9 hypothesis in the first case. Now, three numbers lining up is not the strongest argument in the world, but if we find more sednoids that all have aligned arguments of perihelion, when you integrate them backward 4.5 billion years, that would be a very strong argument that there was an escaped planet from our solar system which disrupted the solar system as it left, and that those disrupted objects have been spinning around very slowly through a process called secular. I don't remember the second word. Anyway, One of those tough processes that acts over billions of years, secular precession, that's what it is, and made a couple of orbits of the solar system in that time.
And remember that I said early on that we can form our solar system with 5 giant planets or 6 giant planets. So once again, this is not impossible. If we had our solar system start with 5 planets, 1 gets kicked out, in just the right way, this could happen. If we start a solar system with 6 planets, we can also make this happen. But also there's a possibility that planets from other solar systems that basically had the same types of processes, they were formed and they were eventually kicked out, passing through our solar system could also cause something like this. And we now know that there's a big population of planets floating in the Milky Way. So hey, that's a cool idea.
There are also a whole bunch of Planet 9 hypotheses that are modified a little, slightly different than the original Planet 9 hypothesis. Different orbits and masses and locations of this planet can explain different parts of the evidence we see. There hasn't been a single choice that has explained everything that we've seen, but especially in the distant Kuiper belt, so we're talking about orbits only 200 AU from the sun rather than the 500, 600, 700 AU that Planet 9 is hypothesized at, could explain a whole bunch of the evidence that was proposed without creating all of the problems that we see. There isn't a single best choice right now, but because there's just too many options for orbits and masses to integrate every possible one. But as computers get better and faster and more time is spent on this, we should be able to pare down the parameter space and reject some of these hypotheses.
And I have 2 comments about this hypothesis. First is that it produces objects that are slightly different from the giant Planet 9 hypothesis. So basically, once we start discovering many more of these things, without discovering the planet, we could actually go and try to verify and say, hey, so if we have a planet like this, it's doing this, we have a planet like that, it's doing that, we can actually see and say whether these are 2 different planets or not and which one is right. Also, my money is on this hypothesis, not because I believe that there's a new planet out there, but because the person who came up with the hypothesis is Brazilian like me, so you have to have to take these things into account.
And then the last of the alternative hypotheses follows in the same thread of reasoning that's used by astronomers often. So we believe that there's this effect out here. We see something happening. There's a clustering. There's an anomaly. But we can't find the thing causing this anomaly. So we're going to say it's out there. It's dark something. Maybe Planet 9, there is this mass out there. We couldn't find it with all these surveys because it doesn't emit any light. Maybe it's a black hole. Now, black holes in general, the ones that we see, form either from the collapse of massive stars, in which case they tend to be 1, 5, 10 solar masses, or they sit at the centers of galaxies. They're active galactic nuclei. They're supermassive. They're millions of solar masses. We don't know of any 5 Earth mass black holes at the moment, but there are hypotheses in cosmology mostly cosmology that say that there should have been some black holes formed by the Big Bang, and those black holes don't have any size constraints on them. And so if you listen to the cosmologists, or at least if you listen to a couple of the cosmologists, and you say there should be some black holes of unknown size floating around, maybe everything in our solar system can be explained by having one of those orbiting on a Planet 9 orbit with about 5 Earth masses of mass. This is one of the few, maybe the only 2-scale image shown in an astronomy slideshow. A 5 Earth mass black hole would have a radius of 5 centimeters. That's how dense those are. 5 Earth masses right in there.
And one cool thing about this primordial black hole hypothesis is that it also solves another problem. It has been, so basically, we measure stars. We're talking here about measuring rocks, etc., but astronomers also like to measure stars. And when you have something passing in front of a star, if it's something like a black hole, the gravitational effects will make the star go brighter and then go fainter. And this is something that people have seen. And one of the easiest explanations for this is if there's a large population of basically black holes that are around the same size. and then it's kind of the same story that we're talking about here. One of these was captured into the solar system. So that's something that could happen. It's also not completely impossible. Another kind of wild thing about this hypothesis is that, okay, sure, we didn't find planet 9, but it's very clear there's a clustering there. How the hell do we find this thing? And my favorite hypothesis for finding this thing is you spend basically all the money in the world. You send a bunch of very small spaceships spherically distributed around the solar system, and you start. I know it's wacky, right? And and then you start measuring basically the same kind of thing that Jake was talking about Cassini. You start measuring the differences in their positions given the expected solar system. The problem with this is that if this is the case, I think this is quite possibly the worst case scenario. The second being planet 9 is on the plane of the Milky Way. If this is the worst case, if this is the real thing, I'm pretty sure that I will not know the answer, which is kind of disturbing because we would only know this by like the 2200s or something like that.
So we've got a whole bunch of hypotheses. We've got some data. What can we do to disprove or validate some of these hypotheses?
So, all right. We've been talking here about all sorts of experiments that we have done. Let's talk about an experiment that we'll do, because some of you asked this already. And I've been alluding to this, and Jake has been alluding to this. What if we had a telescope that would actually find this thing? And this is what we're doing. You went to slides, yeah, thanks. This is the Very Rubin Observatory. This is a telescope that if you walk around the astronomy department at UW, you see mentions to it everywhere, because people here have been working on this thing for something like 20 years already. This is a very expensive telescope. We're talking $1 billion. This is a major project. Basically, all of the US is involved, in Chile and a few others. And this will be basically, this is basically our best bet to finding planet 9. The way that the Rubin Observatory will work is it will measure the entire sky that's available to it. It's in Chile, so it's basically the southern sky. Twice every night, then come back every 3 days, and then it's going to do this for 10 years. That sounds impressive. That's amazing. That's something that, you talk to this an astronomer that does the kind of things we do, everyone gets excited. And one of the things that this observatory will do is try to complete an inventory of the solar system. That's why we got this like $1 billion that I'm talking about. We promised NSF and others that, oh, hey, we're going to basically find everything that is there to be found in the solar system. Can you go to the next slide, Jake? And okay, so yeah, this sounds impressive, etc. This sounds like a big project, but here's the actually cool thing. It starts next year. So in 2025, if everything goes right, we'll start taking data in full operations mode. Once LSSC starts, in at most 2 years, we'll know the answer. We'll either have found planet 9, so say in 2027, there will be 9 planets in the solar system, or we'll know that this is over and there's nothing else to be done. I think that's a good place for us to stop.
Ah, thank you. I think we've got time for a few more questions. Yeah, one back there.
Like whether it's now an apogee or perigee moment. So like with these methods, it be validated for.
Yeah, so let's see if I have any of the, I don't think we included any of the Planet 9 parameter space charts here.
I think, yes, this one, but it's very hard to see, unfortunately.
Okay, yeah, okay. Yeah. So the, oh yeah, each one of those super faint ellipses on the left side, at the very, behind all those objects is a hypothesized orbit of planet 9. Even if you can't see it, I'll just tell you there are no dots on that. It's all ellipses. So we are hypothesizing orbits. We are not hypothesizing positions. Nothing about the long-term effect of planet 9 on the solar system reveals its current position. It could have done, 1,000 orbits, 1,001, 1,025. Anywhere within that last orbit it's taken is so small of an effect over the long-term history of the solar system, that we have no information about that. The big Planet 9 papers all talk about just 5 orbital parameters instead of 6. They completely ignore the potential of trying to figure that out. It does constrain how bright the object is, and it constrains that by a pretty big factor. Could be a factor of, I don't know, 5, 10. So we hope it's close, because that would be real convenient. But the last planetary discovery used up all of our luck. Neptune was discovered when Neptune and Uranus were right next to each other. That was perfect. That was the best time it could have possibly been. We wouldn't have found it for another few decades at least if it weren't for that. So, you know, sometimes you get lucky, sometimes you don't. Who knows where it is?
And this is why I am so sad about the Cassini thing. Because something like the Cassini experiment could actually tell us in which region of the sky it was, instead of what kind of orbit it has. But unfortunately, as we said, basically the data analysis doesn't actually tell us anything. The problem with this predicting the actual position is that there is one nightmare scenario. This nightmare scenario is kind of as bad, or a little bit less bad than the primordial black hole case. One of the prime locations where Planet 9 could be is right on the plane of the Milky Way. So the problem with that is that there are so many stars. We're talking billions, if not more, stars. And if you want to see one dot moving in front of a shit ton of stars, it's impossible. People try. It is incredibly hard. I don't know if we have computing time in the world to actually find something like this. So that's I think I would say that in the reasonable cases, this is my nightmare scenario.
Yeah, right back there.
Solar system to see a lot of mini Neptunes or super Earths. Can you make like a statistical argument that something like that should exist within our solar system?
We see a lot of, so we found a whole bunch of planets in other solar systems, something like 5,000. That set is really, really observationally biased towards the easy to discover planets. And in general, big planets are easy to discover. Planets that are close to their stars are easy to discover. So we found a whole bunch of hot Jupiters. We found a whole bunch of gas giants. There's not much that can be said, as far as I understand, about the overall population of what all sorts of planets can be like, from the current known population of super Earths or mini Neptunes, because we just haven't found Earth-like or Mercury-like planets in other solar systems. So we can't make that sort of statement.
Yeah, and but the flip side of this is that it's interesting, right? So we know that there are all of these other types of planets that we don't have here. So then the question becomes, don't we have something like this here because it was kicked out, or it's Planet 9 or something like that? Or something different happened in the solar system that produced these different types of planets. We didn't talk here about formations for Planet 9, except for basically we start a solar system with 5 planets and then this thing gets kicked out. But actually, where people who do Planet 9 theory are putting their money on is that when Planet 9 is discovered, it's going to be very clear that it was captured from another solar system. So then that's where your argument comes and becomes really important, because we're seeing that there are all these other types of planets out there, and they're fairly common to some observational effect. So it is likely that if it's a capture, it could be something like that. The other thing is that I think it was in 2022, I'm not actually sure, but 2022 plus or minus a year, an exoplanet that has an orbit very similar to Planet 9 was found. It was at something like 700 AU away from the sun or whatever. So it's a very distant orbit, very eccentric, somewhat inclined. So we know that something like this exists out there because we've seen it. So then once again, that's where the exoplanet community can inform us here.
I think we've got time for one more question. Yeah?
This is so cool at the end. You've got potential for a screenplay. We could do it for a start. We could lose that battle for Mr. Spock.
Yeah, so next time that we do this, we should bring actual swords.
Okay, well, thank you all for coming. We'll stick around. Yeah, thank you for coming.
thank you to our speakers and to you guys for showing up here today. Our next Astronaut Tap is August 21st. That's the third Wednesday of the month. I know it's typically the fourth, but it has to be the third due to scheduling reasons. But thank you so much for coming out. And once again, big thanks to our speakers. We'll see you next time.
There was a lot that went on tonight that was assumed knowledge that I don't really have. But
And if you want trivia, come up to the
Thanks
front
for coming out.
we know that there is an object.
Say it again?
Yeah,
Oh, yeah. We don't usually get movies about science, and I'm so excited for the actual work we do. Yeah. There's been a lot of good debates.
If there is some explanation for that, it is way out.